Students, we are going to discuss the concept called temporal models. So, agents in uncertain environment must be able to keep track of the current state of the environment just as logical agents must. The task is made more difficult by partial and noisy percepts and uncertainty about how the environment changes over time. At best, the agent will be able to obtain only a probabilistic assessment of the current situation. There is a need for the representations and inference algorithms that makes that assessment possible, building on the ideas. First one, time and uncertainty. A changing world is modeled using a random variable for each aspect of the world state at each point in time. The relations among these variables describes how the state evolves. Example, diabetic patients. The evidence such as recent insulin doses, food intake, blood sugar measurements, and other physical signs are considered. The task is to assess the current state of the patient, including the actual blood sugar level and insulin levels. Given this information, the doctor makes a decision about the patient's food intake and insulin dose. Blood sugar levels and measurements thereof can change rapidly over time, depending on one's recent food intake and insulin doses, one's metabolic activities, the time of day, and so on. As assess the current state from the history of evidence and to predict the outcomes of treatment actions, we must model these changes. Second stage and observations. The process of change can be viewed as a series of snapshots, each of which describes the state of the world at a particular time. Each snapshot or time slice contains a set of random variables, some of which are observable and some of which are not. So x of t to denote the set of unobservable state variables at time t, and e of t to denote the set of observable evidence variables. The observation at time t is t of t is equal to e of t for some set of values of t. Example, observing raining. Suppose you are the security guard at some secret undergoing installations. You want to know either it's raining today, but you are only access to the outside world occurs each moving when you see the director coming in with or without an umbrella. For every day t, the set t of t, e of t thus contain a single evidence variable u of t, whether the umbrella appears, and the set of x of t contains a single state variable r of t, either whether it is raining, that is x of t is equal to r of t and e of t is equal to u of t. Other problems can involve larger set of variables. In the diabetes example, we might have evidence variables such as measured blood sugars and pulse rates, and state variables such as blood sugar of T and stomach content of T. For diabetics, monitoring a suitable interval might be an hour rather than a day. So it is assumed a fixed finite interval. This means that time can be labeled by integers. So it is also assumed that the state sequence starts at t is equal to 0 for various uninteresting reasons. We will assume that evidence starts arriving at t is equal to 1 rather than t is equal to 0. We will use the notation a is to b to denote the sequence of integers from a to b inclusive, and the notation x of a is to b to denote the corresponding set of variables from x of a to x of b. For example, u of 1 is to 3 corresponds to the variables u of 1, u of 2, u of 3. Then second point is stationary process and Markov assumptions. With the set of states and evidence variables for a given problem decided on, the next step is to specify the dependencies among the variables. One obvious choice is to order the variables in their natural temporal order since cause usually precedes effect, and we prefer to add the variables in causal order as the set of variables is unbounded because it includes the state and evidence variables for every time slices problems. First, we might have to specify an unbounded number of conditions, conditional probability table. One, each variable is in each slice. Second, each one might involve an unbounded number of parents. The first problem is solved by assuming that changes in the world state are caused by a stationary process, that is, the process of change that is governed by laws that do not themselves change over time. The second problem, that of handling the potentially infinite number of patients, is solved by making them make what is called a Markov assumption. That is that the current state depends on only finite history of the previous states. Then the process satisfying this assumption we first studied in depth by the Russian statistic Andrew Markov and are called Markov process or Markov chain. They come in various flavors. Simple in the first order Markov process, in which the current state depends only on the previous state and not on any early states. Using our notations, the corresponding conditional dependence assumption state that for all t of p of x of t divided by x of t is to t minus 1, which is equal to probability of x of t divided by x of t minus 1. Hence, in a first order Markov process, the law describing how the state evolves over time and constrained entirely within the conditional distribution p of t divided by p of x of t minus 1, which we call this as the transition model for the first process. So the transition model for a second order Markov process is the conditional distributions p of x of t divided by x of t minus 2, comma, x of t minus 1. The diagram for first order and second order Markov model is given below. In addition to restricting the parents of the state variables x of t, we must restrict the parents of the evidence variables t. Typically, we will assume that the evidence variables at time t depends only on the current state. So thus the conditional distribution P of E t divided by xt is called the sensor models or observation models. In addition to the transition models and sensor models, we need to specify a prior probability of P of x naught over the states at time naught. These three distributions combined with the conditional independence assertions in equation 1 and equation 2 give us a specification of the. So this is an example concept of Bayesian networks. And the next point is inferences in temporal models. So various inference tasks are: first one filtering, second one predictions, and third one smoothing, and the last one is most likely explanations. Then that the first one fix filtering p of x of t by e 1 is to 2 t to compute the current belief state given all evidence. The above better name state elimination estimation. Example: in the umbrella example, this would mean computing the probability of rain today given all the observations of the umbrella carries made so far. Predictions: p of x t plus k divided by e of 1 is to t for k greater than 0 to compute a future belief state given current evidence. It's like filtering without all evidence. Example: in the umbrella example, this might mean computing the probability of rain 3 days from now given all the observations of the umbrella carries made so far. Prediction is useful for evaluating possible course of actions. Smoothing: p of xk divided by e of 1 is to t for 0 less than or equal to k less than or equal to t. to compute a better estimate of past states. For example, in the umbrella example, it might mean computing the probability that it rained last Wednesday, given all the observations of the umbrella carries make up to today. The last one is the most likely explanation. Argmax x of 1 is to t, p of x 1 is to t divided by e of 1 is to t, to compute the state sequence that is most likely given the evidence. For example, if the umbrella appears on each of the first 3 days and is absent on the fourth, then the most likely explanation is that it remains on the first 3 days and did not rain on the fourth. So these are the concepts of